Okay, so this question asks us to find the minimizer x bar. So we're given a bunch of vectors in Rn, so p vectors in Rn, and we want to find the x bar that minimize this sum of the squared norms. And that's the first part of the question. The second part says that use the second order sufficient condition to show that x bar is a strictly local minimizer. Okay, so we first check, find the minimizer of this. So let's define this as a function of f x bar. So f of x bar is defined as this quantity here, and then we can take the gradient of f with respect to x bar, then essentially take the gradient of x of this with respect to x bar for each of these terms and take the sum, right? Because the gradient or derivative is linear, so we can just take each of the terms separately and then sum together. So the gradient of that is this. So let me show the concept here. So I want to remember that if f of x is written in this way, okay, this is it's kind of special for type of function, but it's used a lot in practice. Okay, you better be familiar with if you see a function f of this form, you just immediately can write down the gradient notation. So what that function is. So this function can be written as a quadratic function, as we did before, and then we can use the derivative of quadratic functions or gradient of quadratic function to find out the gradient of this one here. So to do that, we just need to break the norm, and we'll end up with this. Okay, I want you to verify that. So it's like when we have ax plus b squared, what do you get? Right, it should be a squared x squared plus 2ab x plus b squared. Right, it's pretty similar to this. And we have 1/2 in the front, so that's why we cancel the sum of the 2's. And we'll get that. Okay, and then you can see that this 1/2 times this is pretty nice. This is what we wanted. This will be the q we wanted. And this part will be the new b, which is a transpose times b. So it will be the vector multiplied by x. And this is a constant term, which we don't care. When we take the gradient, then there will be just the qx minus whatever this vector is. So I want it to be a column vector, so I put a transpose of that, so a transpose b, and that's just this. Okay, so now you can see that's the gradient of f, where f is this. So you can look at this. They both have this a transpose term, so I can pull them out, and we'll have ax minus b inside. So that's how we get a transpose times the vector ax minus b. Okay, and also because this is the q, so when I take the Hessian of f, I should just have this q left, and that's just my Hessian a transpose a. So for a like this kind of function, the square of ax minus b, and you put a 1/2 in the front just to make things cleaner later. For this kind of function, the gradient is essentially just keep the ax minus b inside and put a negative a in front. So it's pretty much like this. Okay, so just that, and then the gradient, the Hessian will be just this. So a specific case or special case, the A is identity matrix. So in that case, we'll have the f of x equals that. So the gradient will be, this will be just the identity. So I will just have I x minus b, which is just x minus b. And the I in the front is just the identity. So I have I x minus b for this. And the Hessian of that will be just I transpose I, which is just I here. Okay, so for this simple function, the gradient and the Hessian are even easier. So that's the case for here. So this is like x minus b squared. So if I take the gradient, I will get just x bar minus b. And since I didn't have 1/2 here, so I will have a 2 multiplied here. So this just the gradient of that is just this. Okay, so now we can get the gradient of f at x bar and solve for x bar. So we take this and set to 0. And then you can see that all these terms, we can break the difference. So we can take the sum of this, and then take the sum of this, and take the difference of the two, right? So I keep. You can see that this here gives us just p times x bar. Okay, and here this gives me that sum of xi's. Okay, so if I cancel out this, because this is a constant, then I will just have p times x bar minus the sum of xi's. So I put the sum of xi's on the right, px bar on the left, and then I solve for x bar, which is just this. And that's not quite surprising, it's just the average of the xi's. Okay, so the only point x bar that minimizes the squared distance to all the points is the average of xi's. Okay, just this. So that's answered the first question. The second question is to use the second order sufficient condition to check the x bar is the strict local minimizer. Okay, we just need to check the Hessian is positive definite. Remember that the Hessian of this problem, so you can see that this is the gradient of f. So if I take the gradient with respect to x one more time, I'll see that this will give me, remember that the gradient of this is just 2 times x bar minus xi. I'll take the Hessian of that, just 2 times I, right? As we said at the beginning, right here. The gradient will be just I, but we didn't have 1/2, so when we take the Hessian of that, or Hessian of that, we should just get a 2i. So you take the Hessian of gradient of fi, each term gives us a 2i. So take the sum of p terms and divided by p, that's just 2i. But 2i is definitely a positive definite matrix, right? So that's why this x bar must be a strict local minimizer. Okay, so that's how to solve this question.